It's funny that that just happened, because do you know what I just said? I said, oh, I'm all hooked up here, but I can't help but feel like I'm forgetting to do something. Anyway, let's go ahead and get this going. Alright. Compute. Help compute. Stop all the downloading, okay? It's warm in here, gee. Okay, so today's date and time, it is March 18th, 2023, and the time is, I hate 24-hour time, 12, 13, 14, 15 o'clock, and 14 minutes. Do I sweat when I take a dump? Sometimes. Finish my CMOS. The problem isn't the CMOS battery. The problem is the connector to the motherboard for the CMOS battery got ripped off. So, yeah. Yeah. I'm misaligned. It's a little better. Computer. Computer. There it goes.
Ding, 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 ding. Welcome to Windows 98. Why are you still using Windows 98? What is wrong with you? Stop buying computers from thrift stores, man!
Alright, gamers. So, last we left off... Wow, Jesus. Last we left off, we were having a lot of problems with... Thank you for reminding Warp Track, I'll do that. We were having problems, because we got... climbing, more or less, done. Sorry, my cat is being, like, stupid as hell over there. We got climbing more or less done. We can climb around walls and shit. And we're at the point where we need to do web. So far what we have with web... Come on. How funny would it be if it didn't load, like, ever again? Okay. So far what we have with web... Well, climbing... See, climbing works... It works as well as you can expect for a click-and-play game. You know? Obviously, it's not perfect, but considering click-and-play is not supposed to do this shit, like, ever, we're doing okay. So, in terms of web, what we have done so far... We have, like, this artificial web line that draws... and we'll follow Peter around. Pachuco! Stop that! He's being a little monster. So we have that. Now the problem is, we now need... Where's that cat? Gamers, I have to talk to this cat. I have to talk to this cat. Give me a moment. Pachuco, what are you doing? Stop that! Cut it out! You're being a little monster! You're being a little beast! Cease! I think we got that sorted out. Alright, yeah, so we have a fucking thing. But now we need... swinging. We need to actual swing. So, swinging is basically, you know, a circle. We just have to move Peter in a circle around that anchor point. So to do that, we need to calculate sine and cosine, and I was having trouble with that. So I got this set up where we're using the alterable values of an animation to store sine and cosine values in a lookup table. But every 90 degrees, bloop, bloop, it ploops into the wrong position for one frame. No matter what. No matter fucking what. It does that. Which is horrible. And it's not going to work for what we're doing. So, I looked at a lot of possibilities for what we could do. And I wasn't finding anything... Sorry, looking at my cat. I wasn't finding anything clean and good. So far, I've not been able to fix this blip issue. I believe it has something to do with how Click and Play processes the ordering of the events. But I'm not sure how. So instead, I have concocted a workaround. Toby, relax. Growling for no reason. This is my stinky, dirty, smelly workaround. So, you can see the indicator, the blue blinking thing, is what we had in the previous frame. It still moves following the same logic we have. But you see how there's a little red guy in the middle of him? So I have this red guy set up so that as long as he is within the space occupied by that blue guy, he will follow the blue guy around. So with that in place, if we cross these 90-degree borders, the blue guy is still going to blink into the incorrect position. But the red guy, who is set to only follow the blue guy if he's within his space, will not. The red guy will wait back in the last valid position. So let's watch him. And you'll see the blue guy blinks ahead, but the red guy never follows. So this is a workaround, and it sucks, and it's not a true solution, but for our purposes, it's going to work. And the annoying thing is that I tried to do this with a single line of code that said as long as red guy is overlapping the blue guy, move him around. And guess what? That didn't work. Red guy would follow blue guy regardless, even if he blipped somewhere else. So I ended up having to just do a quick if position is greater than, position is less than, blah blah blah. And that made it work. One more thing. I have added this number right here. This is being used to calculate the distance between our guy and the anchor point. So now, I can change that with the arrow keys, and you can kind of get, see, we're changing the distance. So you kind of get how the swing mechanic is going to start working. See? We can change distance, we can get closer and further from it, spiral in, spiral out. So that's neat. Now, obviously, having to deal with the limitations of this workaround means we kind of have to work with that target point being a certain size, our little guy being a little inaccurate, but at the end of the day, it's going to be fine. Because we're able to do the rotation. It's going to be accurate enough. It's going to be accurate enough. So, looking at the event, I shrunk things down while I was working. This is just under 24 events. And some of them are taken up by control events, so they're not really a part of it. And these few, values and active objects are all that's really being used here. So, what about the active objects? We're only using 1, 2, 3, 4, 5 active objects to do this. So it's like nothing. It's like jack shit. This is probably the cleanest way we can do it, and if it weren't for this stupid 90-degree glitch that we had to put this workaround in, this would pretty much be perfect. So this is what we are going to try to integrate into Spider-Man. And this is going to be tricky to do. So, okay, let me get this is way too small. Let me get this back to how it looked before so we can actually see what we're doing. There we go. Okay. But it's going to be tricky to kind of well, I say copy over. We're basically going to be recreating a bunch of these events. And it's going to be tricky. How do I want to do this? How do I want to do this? I don't think I can have 2 instances of Click and Play open at once. Let me check. Game over here. Maybe I can. I can. Okay, well, we'll just do some back and forth and see what happens. Okay. Okay, this is gonna be tricky, but... Okay, so we have to import that active object over here. Because that one active object, this one right here, this lookup table, this contains, inside of its action point, this contains all of the sine and cosine lookup values. So we need that. We'll go to Click and Play Schools. We are going to Objects. Pick objects from a game. So we're going to pick an object from Secret. All the way to the last level, which is where we're working. And lookup table. That's what we need. So grab it. It's a little blue pixel. You probably can't see them. So I'm just going to plop them up here. Bam. Okay. And what we want is... Why do I not have a start of level event? Why do I not have a start of level event? Ugh. Okay, hold on. We need a start of level event. That's kind of important. Start of level. Let's drag this fucker all the way to the top. Okay, star levels at the top. Let's go back to density. Okay, so at the start of the level, we have to position the lookup table at 0, 0. The only way it'll work. Alright. So now we have to start basically mimicking a bunch of shit. We need these values. So, we need all those values, so let's see. Make sure we're not overlapping. We have 2 counters that are just temporary objects. We have the holding button, which is a horrible workaround for some bullshit that this thing doesn't handle right. Okay. Pop a quick save. And we're going to import those objects. Okay, so we need actual direction, working direction, sine, cosine, don't need text, distance value, and we need y. Distance. Oh, I feel like... No, that was the only invisible. I felt like I had another invisible one. I don't remember. Hidden, I mean. Okay. Anchor. Target. do need a target object. Let's just grab it and we'll, you know, adjust its appearance real quick. We don't need it to be super visible. One pixel. All we need for this shit. Oh. That's gonna be the target. Okay. At the start of the frame, just in case, we're gonna destroy target, position that sucker. Okay. Now we have to start setting up events. Okay, so, to do this, before we do anything, we're gonna need a Peter object specifically for swinging. What do we have so far? Regular Peter, right wall, left wall, top wall. Okay, so that means we need to do the Peter swing. Let's go get a graphic for that. We'll save and then go get a graphic.
Oh.
I'm on ThinkPad. There you go. There he is. Old Bone Legs Parker. Okay. None of these really look like he's web swinging. What does he look like when he web swings in the DOS game? Because this doesn't seem correct. Like, where's the graphic? Okay, get to a good spot, and then we're gonna swing. Oh, that's just a chunk of his crouching animation. Yeah, he just uses a chunk of his crouching animation. Okay. We can do that. Wait. Is that a chunk of his crouching animation? I need to take a screenshot. My brain just, like, farted. Hold on. Press print screen. I don't know if that's going to work in DOS. Nice. Okay. Oh, what we got here? He's just kind of gripping on there. Where's the associated spring? He has like one hand forward, one hand down. Is it? This might be it. Let me look. That's it. Yep. Those are identical. Okay.
Holy crap.
That's what we want. Make our swinging Peter object. Alright, real quick, how was I doing the hotspot, Peter? Hotspot's at his feet. Okay. An action point. Okay. Hotspot will go at his feet. Well, in this case, at his ass. And action point up. We'll do the center for now. Swinging Peter. Okay. Hold on. Looking at the code. So you want the web line to attach to swinging Peter now instead of standing Peter. So let me just look here. Okay, that's clean. This needs to change. Okay, so. God damn it. Oh. Get rid of this sucker. Change this to check swinging Peter. Okay. So the web is redone to focus from swinging Peter. So we need to create swinging Peter. When that collides, we're going to destroy any existing Peters. We'll create a Peter relevant to bottom side. Let's say -2 from bottom side. Okay, let's see real quick what this does so far. Oops. Alright, it made the swing Peter, but notice there's no web. Probably because we have that second Peter. So let me save and get rid of this second swinging Peter. And we'll try this again. There we go. You see that web come out? Okay. So far so good. So far so good. So far so good. Okay. Let me play with this a little bit. See that? It took a second, but it happened. Shot the web, moved. That's where it went that time. Ah, see that? Oh, should not be able to shoot web down, but we'll figure that out. We'll figure that out later. Okay. So he gets created. Good. Now we need a debug object that's going to act as old Blinky over here in our game. Could even just use old Blinky here, so let's see. Not that. Can function as a debug object for us. Swing point? We'll name it that for now, it doesn't really matter. Okay. And now is when we have to start transferring over some code. And this is where shit's gonna start to suck. Starter level, we're positioned to lookup table at 0. And that's all we're doing. We're making the thing blink as well, but that's not important. That's not a real thing. We need some buttons to let us swing a bit. The way it's set up right now, we can just rotate as much as we want, which obviously is not what we're going to want in the actual game. You know, we're going to want to be limited to how we're able to swing. No, I'm thinking of something here. So, the angle here we need to start, like, as soon as he goes into swinging mode, we need to get the angle and the distance that swinging Peter is from the web point. So whereas right now, we have the angle, we have the distance, and we're calculating the left and right, now we want to do the reverse. With the left and right, we want the other two values. So this is some high school math. So let me look it up real quick. Okay, so calculate right triangle. Okay, let's see. Okay, so given B and A, we want the rest. Okay, so let's see what the formula for this would be. Given two sides. So that part's easy. The length, the distance from Peter to the thing is just a squared plus b squared equals c squared. That's just a Pythagorean theorem. You learned that in fucking elementary school. So how did we get the angle? Want angle A. Okay, sorry. My brain is chugging a bit. We want to calculate. Okay, we can get... Hold on. Let me just stop just babbling and actually be smart. Okay. Right triangle. Right, we have... Oh, that's wrong. We have side A, that's an A, shut up. We have side B, that's a B, shut up. And we have side C. Okay? And then we have down here, we have angle A. Okay? Alright. Now this over here, we know this angle opposite is always 90 degrees. We know that, because it's a right triangle. This is basic baby idiot, stupid baby idiot, sucks their thumb stuff. So, with sine and cosine, when we're doing our dinkle here, we're starting at a basis where we know A. We know the angle over here. We're gonna, we like, started at 0. And we know C. We're starting at like 128 pixels. And then we're calculating B and C using sine and cosine. Okay? So, to get A, we're taking the length and multiplying it by the sine of A. Sine of A. And to get B, we're taking the length and multiplying it by the cosine of B. I'm sorry, the cosine of A. And that is how we are getting where to position this point from here. Because all we're really doing is we're calculating a triangle. We're figuring out how far to the right and how far to the up we have to put this guy in relation to this sucker down here. And we're using that with the angle and the length. So all we're doing is we're drawing a right triangle around this point. But we're doing this. Hold on. I like that. Okay, so now we want to start from here, but we need to determine our starting point. So right now, we need to get the angle that Peter is from the web point and the length of this web line so that we can start. And we need to get that from the known, from what we know now. We know A and B. A and B is, you know, how far to the right, and then how far up to get to that point. So we have A and B. So we have to get the other ones. And now I have to remember or look up how it is to work backwards. So, okay, so to get the length of C, so A squared plus B squared equals C squared. Which means C is going to be the square root of A squared plus B squared. Whew. Oh, Lord. Okay, so, oh god. And I'm sorry, I'm having to like reach back in my brain to remember all this basic middle school math. So the square of 6 is 6 multiplied by 6, right? The square of 5 is 5 times 5, right? So theoretically, that's as simple as just multiplying the value by itself. So we have, so we take, so A is going to be, A right here is going to be, the vertical distance between Peter and the web point. And B is going to be the horizontal distance between Peter and the web point. That is easy. So that means, so once we have that value, we're going to have, we'll need to take that value and get the square root of it. So, let me look that up. We're going to have to do some division, I think. Trying to find how to do square root, like division or whatever. How do you do square root without a square root button on your calculator? No? Find the square root of a whole number. Divide the whole number by numbers until you get an answer that's the same as the number you used to divide. It doesn't mean anything to me. How do you manually get the square root? Squaring is easy. How do you do this? Also, let me double check just to verify I'm not being a big stupid idiot. We have modulus. I was checking to see if maybe we had square root. We don't. We have modulus. God damn it. Prime factorization. Find factors of the number and then pairing the common numbers in a pair of two. Too complicated for click and play. Long division. Break the number into pairs. God. Is there not a simple way to get the square root of something without having, like, to sit here and put together a whole fucking formula? Okay, calculate square root. Do fast inverse square root and click. I don't know how to do that though. What's a fast inverse square root? I never fucking thought of this. I never thought of, like... I never considered that I would have to calculate square root. At no point did it cross my mind when I was doing this. I don't know why it never crossed my mind, because obviously I'm going to need to calculate the square root. You forgot what square root is? I mean... little. Fast inverse square root, an algorithm that estimates 1 over the square root of x. Okay, I'm looking at source code from Quake 3 Arena of how they implemented fast inverse square root. And this source code includes such lovely comments as, Evil floating point bit level hacking. What the fuck? First, what the fuck was one of the comments? That wasn't a comment from me, it was one of the comments from id Software. Like, one of the comments is just, what the fuck, question mark. They documented... Hold on. God. Yes. What the fuck? I mean, I guess what the fuck? Like, what number is this? What is this supposed to mean? What the fuck? So apparently fast inverse square root is attributed to John Carmack, but John Carmack based it off an unpublished paper. That does explain why there's an example of Quake 3 source code in here. Lord. I'm looking at the algorithms and codes in here, and it all looks like way too complicated to do in Click and Play. There's square root 1. I'm looking at a square root lookup table. I want to do another lookup table. Oh my god, I can't believe I'm getting my asshole kicked in by square roots! I'm getting my butthole kicked in by square roots! Hold on a second. This number up here, this is showing the total number of active objects on screen. I'm going to adjust its calculation. Rather than just the active objects on screen. Where is it? Where is it? We're going to set it to the number of web lines. Okay. Start with one web. There's a web line off screen or something. And fact, let's kill that web line that's off screen. We don't want that. Let's do it programmatically. Let's just, at the start of the frame, let's kill that web line. We actually have a proper amount. Okay, 0 web lines. Shoot up. 19 web lines. Stand under here. 2 web lines. Shoot off to the left just a little bit. 9 web lines. Okay, so here's the thing. Here's the thing. Rather than using the Pythagorean theorem and having to figure out how to calculate the square root in Klik and Play, we could instead estimate a distance, which would be good enough for what we're trying to do, right? 18. Okay, so we know how many web lines are created at any point. See, 18 for that way, 17 for that way, 18 for those, 18 for that kind of distance. Once you get closer, it goes down, 8. So we know how many web lines are being created. Each web line is 12 pixels long. So if there's like 18 web lines on screen, and we multiply it by the 12 long they are, we get 216 as a distance. So we could, rather than using math to calculate C here, count how many web lines we have out, multiply it by the length of the web line, and get a good enough approximation of C. Because here's the thing, we only need to calculate C and angle A once. That's when we first start web swing. Everything else gets taken care of by our sine and cosine calculation. We just need to get those starting values so that we can start to swing. Close some of this shit up. So that's actually, that might work. That might work. Okay, so this is the distance value we're using. You'll notice it's incredibly high. 128,000. Now the reason for that is in the calculations I'm doing, I need to do some decimal level calculations, and Klik and Play does not support decimals. So instead what I'm doing is I basically shifted everything over a few bits, not a few bits, a few decimal places, done the math, and then when I'm done and ready to import the math to positioning, like at the very end, I'm dividing the number by 1,000,000 to get rid of those extra decimals at the end and get it into a proper, scale. So that's why we see 128,000 for the length instead of what it should actually be is 128. These extra 3 zeros at the end, they basically don't exist. They're fake zeros. Okay, just thinking in my head what I gotta do next. Okay, so we can do that to get that. Oh, how do we get the angle of A? Okay, how to find the sides? How to find the angle? Okay. So one way to get the angle of A, right here, given, just the length of all these sides, is we would have to use another kind of math thing. We would need arcsine, arccosine, and or arctan or whatever, and we're obviously not going to do that. We're not going to do that because that's not going to work. We can't have another lookup table in here. This was a big enough pain to do. So instead, we can once again do another estimation. So, go ahead, fire off our web, we're creative. So at this point, don't worry, Warp Drake, you're not supposed to understand all this math. I'm not good at explaining this shit. So at this point, the web line over there, it's looking at the anchor point from Peter. Like, we're using Click and Play to say, look over there. Now, some of them are looking in slightly different directions, as you can see how it gets wiggly up here. But more or less, like, all of them are fine. The one closest to Peter is going to be the most accurate. So in Click and Play, we have 32 directions. What we need is a value, comparable to, that goes up to 360. For 360 degrees. 0. Interesting thing is that Click and Play considers 0 to be the right instead of straight up, and that's kind of annoying. But probably nothing we can't work around. 32. What's 360 divided by 32? 11.25. What's 32 times, let's say, 11? What's 32 times 12? Yeah. 32 times 11 is closer, I think. Obviously, a decimal, just 32 times 11 point whatever we just calculated would be better. But I don't know if it's worth it if we just want to get it accurate enough. So what I want to do is, rather than having to calculate arcsine, arccos, all that bullshit, we take that 32 directional value, we multiply it by 11. Like 8 times 11. Like, almost 90 degrees. It's a little off. And we once again, the same way we're guesstimating the length of C, we'll be guesstimating the angle of A. And that's only going to be relevant, once when we start web swing. And it's going to be a little janky. But it doesn't have to be that accurate. It's just the beginning. The rest of it's going to be handled fine. Okay, so. Counter 0, counter 1. I need 2 counters just for my sake. 2 test counters. Just so I can kind of work out the math. Test length. And test angle. Okay, and we're going to use this to kind of work out what we're doing. Okay, so. There's going to be some test events. So, if the number of web line objects is greater than 0, you're going to set test length to the number of web line objects times 12, since they're 12 long. Let's start with that and see what happens. So right now, it started at 12 because we launched the game with one web object that gets destroyed. Let's fire one off. 180. So the distance between Peter and that web is approximately 180. And of course, one thing to note is that number right there starts at 12. It doesn't just shoot up to 180 immediately. It counts up. And that's because of how we're working this. These lines are getting... Well, you can't tell. They're getting shot out from Peter to up there. So there's travel distance. 16 over there. 108 over there. There's travel distance to account for. 36. So, we would not want to do the calculation until the number of webline objects has stabilized. Basically, after Peter shoots out his web, he needs to stop moving until the number of web lines has stabilized. So we need a way to calculate the stabilization. Basically calculate when the number of web lines has stopped going up and when it has stabilized. Right now it's 4. Right now it's 7. So logically what we would do is we would keep track of how many web lines there are per frame. The next frame will compare the current value to last frame's value. And if they're the same, then more or less it's stabilized. We might have to put a timer so that rather than just comparing for 1 frame, it compares for 2 frames or for 3 frames or whatever. But more or less, that's how we would check for stabilization. Okay, so let's create a counter. Number of web last frame. Of course, there's a limit. Number of web last frame. Alright, so. So if the number of web is greater than 0, we're going to set... Oh, I need to set an icon on this or I'm going to keep getting them mixed up. Hold on. Like, I'm going to get mixed up if I'm not setting this up in a way that I can tell what's happening. It looks like shit, but it's kind of like a spider web. Okay. Okay, so as long as there's more than one of those, we're going to set the counter to the number of web lines. Okay. So that means the comparison to see if it's stabilized has to happen before this event. Otherwise, it's just going to always look stable. So, if the number of swinging Peters is 1, the number of anchor points equals 1, just kind of a double check. And then the number of web lines equals the number of webs from last frame. Once when it loops. For testing purposes, I'm going to have it play a sound. Not that one.
Chicken.
We'll play the chicken sound. Okay, so let's see what happens.
Chicken.
Happened twice.
Chicken. Chicken.
Why is it happening twice?
Chicken. 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 Chicken.
It seems like it's happening once when the first web appears, and then once more once it's actually stable.
Chicken. Chicken.
So how do we get rid of that first one? Hold on a second. I have an idea. Okay, so let's also check to make sure there's more than one of them. Otherwise, it could show as stable even when there are none of them, which we don't want. Let's try that.
Chicken.
Ah, it's still happening twice.
Chicken. 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 Chicken.
I'm trying to think of an easy way, because obviously we could slap in another counter and have that count a certain number of frames and make it so it can't fire off until like 2 or 3 frames have passed, but that's such a dirty way of doing it. What else can I do for this?
Chicken. 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 Chicken.
I'm gonna try something. Take the number of web from last frame. Let's turn it into a regular counter so we can actually see the value. Okay, so top frame is what Click and Play. Top number is what Click and Play thinks the number of web lines is. Bottom number is what it thinks the number of web lines was last frame. Let's look at what the values show.
Chicken. Chicken.
Okay, let me try something. I'm going to delete the one I have here.
Chicken.
I think it was just because I lazily left that one line there, and even though I was, programmatically deleting it, it was still fucking with the comparison.
Chicken.
That makes sense. So that was my bad. That was me being a lazy idiot. Okay. Okay, let's just test a few instances.
Chicken.
Yep.
Chicken.
is detecting it correctly. Now it only fires off once it's done, once it's stabilized.
Chicken.
Good, good, okay. Okay, so we need this check to only happen once when we're not initialized. We need to store the initialization stuff. I could store it inside of Swinging Peter, but we only have three variables on him, and I'm terrified of wasting one for something like this. We have flags or something, I forgot. No, of course not. Flags are in the later versions of Klik Team. What about the anchor point? If I'd use the anchor point, let me see, if I'm using any of the anchor point stuffs, doesn't look like I am. Not. Okay. Over here. What? Okay, so here's the thing. That anchor point has to simulate the anchor for my little test here. Let's see what variables I'm using over here for that anchor. Anchor. Nothing happens to the anchor, but we need to see what variables are being used. So let's see. Counter Y, counter. I don't think I'm using any of its variables. So, okay, let's use the anchor to store the variables for initialization. Okay, so. Got a new thing here. So, this will only happen if anchor point alterable value C equals 0. So, after we're initialized, and we've had our chicken, we're going to set alterable value C to 1 so that it can't do this again for that segment. Alterable value C equals 1, that means we are initialized.
Chicken.
Okay. So at that point, we want to set distance. We will set distance. This is our distance value. We're going to want it to be relative to test length, except a much longer butthole. Let's see.
Chicken.
So it's going to have to be 168 times like what, 1,000,000? Let's check. Set counter to equals, come on, number of web lines times 1,000,000. Let's see if that's it.
Chicken.
Oh, that might be too much. That's way too much. Okay, hold on. 1,000,000 was not the right number. Try 1,000, not 100, 1,000. I'm not good at this. This is simple math, but don't look at me. I'm busy.
Chicken.
1,500. Oh, you know what? I'm doing the math wrong. Doing the fucking math wrong. It's no web line times 12 times like 1,000 or something. We need to get the length of the web line.
Chicken.
There we go. See, 168? It's perfect now. 168 becomes 168,000.
Chicken.
26. There we go. That's what we needed.
chicken,
24. Perfect. Beautiful. That gets initialized when we do that. Next one. Here. To test length and test angles we can end up deleting eventually. Okay, so test angle. We're going to want this to become something comparable to the 360 degrees. So, once we're stabilized, we're going to set, it's going to be another test one. We're going to set angle, set the counter to, and first we're going to get it wrong. First we're going to do the 32 degree thing. So, the current direction of web, and it's probably going to pick a random one or the last one. I don't care what it picks, just as long as it picks something.
chicken,
So it's set to 8 right there. We can see 8 up there. So if we shoot to the right, it should be close to 0.
chicken,
The left, it should be close to 16.
chicken,
It is. And at an angle, it should be something in between.
chicken,
4. Okay. So to turn this into a proper 360 degree value so that we can actually do our calculations, we just need to multiply it by 11 a little bit. But since we don't have decimals here, we're just going to do it by 11 and see how that turns out. So, direction times 11. So this should still be 0.
chicken,
Up should become
chicken,
close to 90. Not quite 90, but close to. Left should be close to 180. Not quite, but close to 180.
chicken,
It is. That angle should be,
chicken,
close to 45 degrees.
chicken,
Close to whatever that is. Okay, so we're getting good values there. Now, one problem, though, is that it's considering 0
chicken,
to be to the right. And 90-ish to be up. I want 0 to be up. And 90 to be... I don't give a shit where 90 is. I think to the right? Let me check how I was doing it. Hold on, let me save real quick. Let me check my test game. Okay, so 0 is up. 90 is to the right. Okay, so theoretically what we have to do, we have to take the value. Take the value, okay? Right now it's set like this. We're going to want to rotate it 90 degrees to the left. And flip it? It might not be that important to flip it. We might be able to get away with some honky-tonk bullshit here. Let's see. Zero. 8. 0. 8. 0. 8. Okay, I have to kind of visualize this. Okay, so we have directions. Click and play. Click and play 0, 8, 16, 24. Which makes this, 32 as well. We want to take this, rotate it a bit, so. It's like that. So we want, so 0 should become 24, 8 should become 0, etc. So to make 16 into 8, we subtract 8. To make 8 into 0, we subtract 8. To make 24 16, subtract 8. 32 into 24 was 8. The problem is this quadrant up here. We're going to have some different math, right? Because, let's look here. This point right here. Approximately, more or less... No, not a pencil, give me a brush. 4. But over here, what we would want that to be is... $28. How do we turn 4 into 28? Not only how do we turn 4 into 28, how do we turn 1? Here. 1, 2, 3, 4, 5, 6, 7. Into their respective numbers. Okay, so think of it this way. So, 0 has to become 24. That's easy. 0 plus 24 is 24. 1 has to become 25. 1 plus 24 is 25. 4 plus 24 is 28. 7 plus 24... 31. Okay. Okay. So if the number is less than 8, we're just adding 24 to it. If it's less than 8, we add 24. If it's more than 8, no, if it's greater than or equal than 8, we subtract 8. Okay, that's how we rotate the ship. That's how we rotate this ship. Okay. Less than 8, add 24. Greater than or equal than 8, subtract 8. Okay, okay. Now, the problem is that if. Then we have to duplicate this event, which I don't really want to do, but I'm gonna have to. I'm gonna have to. Okay, so if the direction of web line is if the direction of web line greater or equal to 8. We're setting it. Before we do, we're gonna discard the times 11 thing. First, we want to reorient shit. And we're gonna take the web line, and we said we're gonna subtract 8, right? Subtract 8. Okay. Minus 8. Okay. Let's test to see how that comes out. So shoot it off to the right. It's not gonna matter because it's not less than 8. Shoot it up. We should, if it calculates 8, we should get 0.
Chicken.
Good so far. Shoot it to the left. If it calculates 16, we should get 8.
Chicken.
We shoot it to the top left, we should get something similar to 4.
Chicken.
That's working. And then we need the condition for when it's less than. And that unfortunately means we're going to have to duplicate this event because of how shitty Quick and Play is. Not a big deal. We're already here. Might as well do it. There might be a better way to do it, but it's not coming to mind right now. So, when this is less than 8, set the sucker as initialized. Or anything else I do back here? Play chicken. Set that fucker. Then this. So. Just adding 24. Okay. See how that comes out. So.
Chicken.
Still get 0.
Chicken.
Still get 8.
Chicken.
Still get 4. So if we shoot off to the right, we should get something close to either 0 or 32. No, I'm sorry. We should get something close to 24.
Chicken.
24. If we shoot up, we should get...
Chicken.
If we shoot up and to the right, we should get something close to 28.
Chicken.
This is working. Okay. This part is working. Now, we have to turn into something close enough for 360-degree rotation. So, that'll... could be an issue, because now we have the issue of click and play not really being great with order of operations. Like, what's it gonna do here? Is it gonna multiply 8? Shit. Okay, let's test real quick. Oh man, I'm not looking forward to this part. Because, as you see, there's no parentheses. No parentheses at all. So if I do times 11 here, order of operations says it's going to multiply 8 by 11, which is not what we want. We want to first do the subtraction, and then multiply that result by 11. The easiest way to do that would be with those parentheses. Half that. Let me do something. This is our testing. Let's grab our real angle, our actual direction, which is off to the right. Let's do this. We're going to set that, what we did, and then the actual direction, we're going to set it to test angle times 11. That way it's a two-step process. Now let's see what happens. Okay, so
Chicken.
0 makes sense.
Chicken.
888, that's good.
Chicken. Chicken.
Good.
Chicken.
Okay. That's working. It unfortunately means we have to keep that variable as a scratch value, just used for the actual calculations. But that should be fine. Let's move this fucker back up here before I lose it. So, test angle has to stay with us. Let's see, test length. Are we still using test length? I think we... I don't think we need test length. Test length can be murdered.
Chicken. Chicken.
Okay. Let's bring our values back down here. Actual direction and distance. Over here. Let's just make sure these still line up. So,
Chicken.
240. Distance, 260 degrees.
Chicken.
180 distance, 0 degrees.
Chicken.
120 distance, 88 degrees.
Chicken.
Oops.
Chicken.
208 degrees, 240 distance. That seems accurate. That seems accurate. Okay, so after that, that means we have the actual direction is set. Our distance is set. Our scratch value was used. So at that point, we should be able to just kind of start bringing these fuckers in. We're already setting that position. We don't need to flash nothing, so start of level is taken care of. These next few events are control events. So let's add in some control events, because we're going to need them for testing this shit. So, left, right, up, and down. Okay, we did it with keyboard here, but we're going to want to do it with joystick in here. So, left, right, up, and okay. So right now we're going to tie them directly into the values. Once we have, the physics of how it should work, we're not going to be doing that. But for now, that's how we're doing it. So what these do is they subtract or add to the counter. The way I have them set up right now, I'm going to do the reverse just because it's going to work better. Well, no, we'll do it this way. Just for now. Okay. Subtract for left, add for right. I'm losing my place. Subtract from 1, add to counter. Top and down goes control the length. They subtract or add 1,000, which is technically just 1, but we're multiplying it up so we can use some decimal. Up is subtract. Okay, had to check. Subtract from counter 1,000. Add to counter 1. Okay. Save every step of the way. Okay. Then we have an always line, which we're going to use to, do some shit. As you do. This is always line. Okay, this always line is creating our target point at the action point of our lookup table. This is what we're using to pull those values that we need. So let's do that. That means we have to have another always. Create target relative to lookup table action 0, 0. Okay. Next. If that target exists, we're going to pull data from it. So, number of targets is greater than 0. I'm not going to destroy it. There's an important order to this. We have to see. So we're going to set sine to its x position and cosine to its y position. And we're doing that because we're positioning it according to the sine cosine lookup table we have built into that object. Sine is x, cosine is y. Okay. X. Y. What else are we doing in it? And then we destroy it after we have those values. Okay. Destroy the target. Good. There's not a lot of events we have to go through here. It's only like 24-ish, so isn't as bad as it looks. So next, so we have our actual direction, which gets set between 0 and 360. But they might be situations where, due to how we have it coded, that number might either go above 360 or below 0. We don't want that. We want to clamp it between, so it can only ever be between 0 and 360 when we're doing calculations. So what we'll do is, if the direction is less than 0, we set the counter to 360 plus its current value. If it's greater than 360, we set the counter to itself minus 360. Okay, so it's less than 0, 360 plus itself. Plus its current value. Now one more for if it's greater than 360. For that, it is itself minus 360. Good. So that clamps our value, and that's vital. Don't want to fall out of that range because we're not set up. Next, we have another always line. And we have multiple alwayses here because remember, for the most part, this code runs in the order that it's set up here. 5 at the top. Event 5 runs before event 6, runs before event 7, etc., etc., etc. So these multiple always means it's going to run in the order we have it placed. This next always, what we're doing is we're setting our working direction to the value of our actual direction. Yeah, exactly, Warp Track. And that's one of the reasons why Click and Play not having comments sucks. If this had a commenting system, it wouldn't be a problem. At all. Let me show you something real quick. Show you real quick, just an example. Get a good example. I'm not very good at this one. Okay, so for example, my wait a sec screen with all our favorite characters jumping around, I make that in Quick Team Fusion. So, Quick Team Fusion's editor right here should look pretty familiar. You can see these blocks with text, leaving comments for myself so I know what the code I did for the wait a sec screen does. So you see, here's all the code for the lawnmower part. Start it. We're setting things randomly. If Lawnmower Man and Jimmy collide, they bounce. They fall off screen. They're off screen. You know, every 2 seconds or so, they're changing direction. They're moving things around, and there's cleanup. So yeah, you probably never knew that, but yeah, the whole wait a sec screen, it's all I've created that inside of Quick Team Fusion, which is just an advanced version of Click and Play for modern computers. See, we have the background. You can see an after image for Juicy Justin up here. You can see we're setting the date. You can see a notification thing I want to set up for showing the stream schedule that I've not finished yet. It's kind of up here because I never got around to finishing it. If you look below, you see the course from the DK portion of the screen laid out. And off on the left here, you can see all the objects that I use when I do it. That's all there. Yeah, so being able to comment your code is great. It's really great. It's more complex than you thought it would. It's really not that complex at all. Like this is super simple. Like, if you spend a few hours just to understand how Fusion works, how Klik Team works, you'd see that this is super simple. I have an explosion here. This explosion. I used it for when Todd explodes. This is the explosion that happens. Let me get back to where I was. And you can kind of see the DNA. Like, this is Klik Team. See all the things, the graphics. And then, you know, you jump back over to Klik Team Fusion. It's basically the same fucking event editor. See what I mean? Like, hold on, let me actually show you, because you're missing the top part. See? It's basically the same fucking thing. Like very little has changed. Like, where's Todd? Let's open Todd. There's Todd. See, there's regular Todd. Then there's very angry Todd. There's annoyed Todd. There's angry Todd. There's mad Todd. He's all there. Anyway, okay, enough of this. Let's get back to what we were doing. Okay, I lost my place. Okay, right, we were talking about this. So, we have a working direction. We're copying over our actual direction over to the working direction. And we're setting what I call our quad to 0. So, the quad is basically telling us which quadrant of a circle we're operating in. And the reason we're doing that is because our lookup table is only calculating up to 90 degrees of sine and cosine. We're doing that for 2 reasons. 1, so we have less data to store. And 2, so that we have a more accurate calculation. Like, the bigger the numbers get as you go around the circle, the more accuracy we're losing with how we're trimming things down for click and play, and the more inaccuracies we're going to get. So instead, we only calculate 90 degrees, and for the rest of the quadrants, we just kind of flip our result to match the quadrant. Okay, so for this always event, we are copying over the direction to our working direction and resetting the quad to 0. Let's do that. That's where I'm at, right? Yes, that's where. Okay, so direction into our working value and reset the quad. Next line. So we're detecting our direction to see if it's greater than 90, greater than 180, greater than 270. That's where we are setting which quad we're working in. So if it's greater than 270 degrees, then we can get it back into that 90 degree constraint by just subtracting 270. And then we set the quad to 3. Same for 180, setting it to 2, for 90, and setting it to 1. Let's do that. Hey, the Sketchified! Thanks for subscribing, appreciate that. Okay, so, direction is greater than 270. Let's start with that. Okay, so we're gonna set the directional value to itself minus 270, if that's the case. Okay. Minus 270. And we're setting our quad to 3. And we'll do the rest. So after 270 comes 80. And the quad for that, I believe, is 2. It is 2. Just wanted to double check. Might as well double check. What's the harm in double checking? Hey, Crab Apples! Wow, thanks for that donation. I appreciate that. that is, I really do appreciate that. That helps Cinco and I out a bit. Like, you know, I have a full-time job, and you know, Cinco works as many hours as she can as a pharmacy, technician. And, we're able to make ends meet, but every once in a while we run into those things where a little bit of extra cash helps. I took my car to Jiffy Lube this morning to get the oil changed, and while I was there, it turns out the, what do you call them? The fuel injectors or whatever needed to be cleaned, so that was another $100-something to get that done, so that was annoying. But got that done, so hopefully my car doesn't shit itself. Little things like that come up, and tiny donations help, but it's, of course, never, never necessary. I have a full-time job, I'm able to make it work, but I still really do appreciate it when it comes in every now and then. Like, back when we had to get... like, the other day, I was looking at my finances because I was kind of annoyed how much money I didn't have. And by how much money I don't have, I mean by how much I still have to pay off for my credit card. And looking at it, like, man, the FIP medicine that we had to get for the cat, that drained the shit out of me. Like, that fucked me up for a little while. I'm recovering, thankfully. And I don't know what I would have done without the donations I got from you guys to help my cat with that, so I'd still appreciate that. But, yeah, that fucked me up a bit. It really did. Ooh, that took my credit card for a ride when that happened. Alright. What's this next block? Okay, so after we set the quadrant, we're then checking if the direction is less than 32, between 32 and 64, or greater than 64. The reason we are doing that comes down to the sine and cosine value that we're storing in lookup table. So we're storing it within these animations. There's 32 animations. And only there's 32 directions to each animation, and only 32 directions to each animation. So we'll go around, see, this is 0, 1, 2, 3, blah, blah, blah. Imperivum propaganda. Thanks for subscribing, I appreciate it. I struggled a bit there, I got it. So each of these directions, as I said before, holds the sine cosine value in the active point. So once you get around to 32, we have to go to another animation for 32 more values. And once we get done with those 64, we go to the last animation that stores the last few values. So that's why we have to determine the direction we're looking at so we can set the correct animation on the lookup. So, the value is less than 32, that's fine. We'll make sure we're playing user animation 1, which holds the first 32 values. And then we make sure that the object is looking in the direction that we calculate. So that's easy. Start with that. So if 360 is less than 32, play user animation 1 and select direction to our working direction. We don't want to do it to our actual direction because our actual direction can be anywhere between 0 and 360. Our working direction has been clamped to between 0 and 90, which is all we have values for, and that's exactly what we want. Okay, next is between 32 and 64. So that greater than or equal to 32, but less than 64. Right? For that, we're going to play user animation 2, and then we're going to set the direction to our working direction minus 32. That way, it gets clamped to the 32 directions that we have values for. So we'll change this to animation 2. Oh, minus 32, not minus 64. No. Minus 32. Good stuff. Okay, the last one, if it's greater than 64, change animation to 3 and set the value to itself minus 64. Itself minus 64. Wait, greater than or equal, right? Yeah, greater than or equal. You want greater than or equal. You don't want to have 64 get ignored. That'll cause problems. Alright. That's those first bits, or anything over there? No. So then we have 2 more always lines that we're running. So, these are to set the B and C value on this object. And we have to separate them into 2 lines, because you can't set B and C twice in one line for one object, due to a limitation of quick. So, the first thing we're doing is we're setting alterable value B of our guy, our little target, to the distance times sine. That's how we're calculating. This is the point where we're starting to calculate where we need to put this guy. So let's get that created. Always. So we're going to set it again. We're going to set it to we're going to set alterable value B, distance times sine. Distance times sine. Okay. Then C is going to be distance times cosine. We're going to need both of them. Bye, Jim Sticky. Thanks for joining us. I need to give my dog his medicine. Give me one moment, gamers. I want to kind of wrap up the code copy because of how tedious it is. I don't want to have to come back and keep doing this next week, so give me a second. We're going to give the dog his medicine. We're going to come back. We're going to try to wrap up this code copy before we wrap up the stream for you. So, bear with me a moment. Back, gamers. Go ahead and plug myself back in. Come on. Alright. Okay. Let's finish this code copy. So we got to do cosine. Okay, so that. Set C to cosine. It is cosine, right? Yes, cosine. Just had to make sure I didn't call it cos. Right? The next line. This is important. We're taking that value B we just set, and we're dividing it by 1,000,000. Because while we were doing the math, we needed to use decimal points. Klik Play does not support decimal points. So instead of losing that position, we just shifted everything over, shift those decimal point values over past the decimal point, did the math, and now we're shifting them back down by dividing it by 1,000,000. We're saying its own value to itself, divide by 1,000,000. Just copy that, that. So, B self divided by 1,000,000. And C is self divided by 1,000,000. Anything else in that line, or is that? Now this block right here, this is what I was talking about earlier. This is my workaround for that glitch where on the quadrants, It's glitching out for one single frame into the wrong position. All this is doing is the X position of this little shit greater than the X position of our glitching out target, minus 16, plus 16, blah, blah, blah. This is just a simple... Our two square... is a point existing inside of this square calculation. Super simple. So... do that here. Where's my position? X position greater than swing points X position minus 16 or less than swing position plus 16. I mean, and. I just touched my glasses. God damn it. And Y position is greater than Y position minus 16. And Y position is less than Y position plus 16. Oops. That was backwards. Hold on. Oh god. Killing it. Help me! Plus 16. There we go. Okay. So if that's true, then we'll position Swing Peter at this fucker. Pop another save. Save glass. And then, at the end, we're going to set the position in respect to the quad. So depending on the quad, you either add X to the B or C, or subtract to the B or C, or whatever. It's kind of a... It's just, you kind of just figure it out and you copy and paste it. So quad 0, 1, 2, and 3 for all 4 quads. So, where's my quad? Where's my quad? 0... we're setting X, the X of the anchor plus its own B. X coordinate 2, X of the anchor plus B. Y will set it to Y of the anchor minus C. That's quad 1. Let's do the other 3 quads. Okay, for quad 2, for quad 1, as opposed to 0, it's plus C plus B. Plus C plus B. C plus B. Next quad, gonna be minus B plus C. Then for the final quad, it's gonna be minus C minus B. At the initialization, once that initialization is done, we need to also position our guy relative to swinging Peter. Okay, I don't expect this to work the first time at all. Let's see what happens.
Chicken.
Okay, so that... God, we're having trouble. Something's not working right.
Chicken.
Oh, look, we caught him! We caught him! Look! Look what's happening! Look at that! It's glitched to fuck and it needs work, but look! We're swinging! let's test the length. Bring it in. Look at that! We're close. Let's stretch him back out. Oh my god. It's glitchy and it needs work. But as a proof of concept, there we go. Look at that shit. We're gonna be able to do it. we have to iron out all the bugs, but we are going to be able to do it. That is incredible. Look at that. I can't think of a more satisfying feeling than putting all that fucking effort into something like that and having it actually more or less work. Let me adjust this. Let's position this instead of at him. Let's position it relative to the bottom side. See if that gets us a better result.
Chicken.
Still a little buggy. A little buggy.
Chicken. Chicken.
I know a quick way we can do it just to get a more satisfying result for now, and we'll have to clean up a bit later. Let's position it at the bumpers, since the bumpers kind of get left behind. And we'll have a more, clean solution next week when we actually start debugging this code.
Chicken.
Or not. Hold on. Probably have the ordering wrong.
Chicken.
Oh, I bet I know what it is, actually. Hold on. Distance and actual directory here. I just want to see. It's probably just
Chicken.
doing it wrong. It needs to be inverted. It needs to be inverted. Because right now, look, this is a circle, okay? The web point right here is the center of the circle. Peter is the edge of the circle. 0 means the top of the circle. So that means that the guy is way up off screen at the top, and Peter's at the bottom. So really what we need is to have him be spawned opposite. We have to have the direction value set opposite. So that's why it's not working right now. Oops. Okay. So that means we know what we have to do to fix this. Well, to get it working better. We know what we have to do. It's just a matter of putting in the time next week to do it. But this is very satisfying to see him swinging around. Let's make him longer. Let's make him a little longer. All the way. Oh! We killed him! We blasted him off screen. Let's try that again.
Chicken.
Oh. Look at that. Look at how fast it goes when you're far away. Oh, we killed it again. I think what's happening is our what's it? Our guy. This guy. This little fucker. This blue guy. When he's disappearing, it's because he's going off screen due to the quad glitch. Because if we quad glitch up here, it's probably trying to put him way up or to the left, which means he's off screen, and Click and Play is going to try to clean him up by killing him. So we go up, we quad glitch, which only happens sometimes. Bam. And he got destroyed. Now that's fine, because in actual practice, you're not going to have a web line that long, because there's just not enough room on screen. Like, when you're actually playing the game, your web line
Chicken.
is going to be a lot shorter. So it'll never quad glitch out.
Chicken. Chicken.
Look at that. Very happy. Very happy we got somewhere. Now, I'm just admiring my work. I'm just admiring it because I'm so happy that it's working out. All those concessions we have to make. Oh, you know what happened there? Our guy, our target, had moved too quickly away from Peter, so they were no longer overlapping. So Peter thinks he's too far away, thinks he's glitching, he's not moving to it. So there's little things we gotta do to tweak it. We gotta increase the error allowed to move Peter with it. We gotta adjust speed. We gotta adjust a lot of shit. But this is the proof of concept. We're able to move Peter around the circle. It's very satisfying. And everyone loves it. Okay. Save this fucker. Beautiful. Absolutely gorgeous.
Holy crap!
Holy moly. What a time that was. Put my tunes here. Very satisfying.
Goodbye, stupid. We've had a lot of fun on your crappy computer. Please don't ever come back.
Alright. Go. Gamers, thanks for tuning in. Thanks for watching. Thanks for sticking through all that bullshit. Tune in on Tuesday at 8 p.m. Eastern for an hour-long mini-stream playing more of the Herbs in the City. Tune in on Friday at 7 p.m. Eastern when we play more Toy Story 3. And then tune in next weekend, Saturday, 1 p.m. Eastern, when we play more Oblivion. And try to fix up Peter's swinging to make it, to try and turn it, you know, iron out the glitches and try to gamify it so we don't just have free reign to spin forever. Alright, gamers, I'm going to eat whatever is in this ball of aluminum. Whatever it is, I'm going to eat. Thanks for watching. At least be decent.